Hi everybody, welcome back to Chem 121. I had to deal with the cats who were playing in the window? I don't know, cats are weird. They both jumped up there and started fighting. Now it's just Maya. Hi, Maya. All right. This is the last lecture. After today, we'll have covered all the content in the class in one form or another. So, we're not really going to do much with the aqueous salts section unless we have time. We might actually have time, but pH and buffers are very important. So we're going to spend the majority of today talking about those so that you will be able to understand those terms when you start, say, cell bio. Okay, let's go ahead and get started. By the way, if you have not requested your exam to be moved to a different day, requesting to move it to Thursday, probably not the best idea at this point. You can still request to move to Saturday, as long as you do this before Friday starts. After Friday, I mean, if you absolutely had to, like, if you emailed me at, like, early on Friday and said, hey, I can't take the exam, I'd be like, oh, all right. Make sure that you do that ASAP, okay? If I deem it too late and I realize that this is kind of arbitrary, there may be a point charge assessed to your score for moving your exam well past the deadline. All right, let's talk about pH. pH is something that most people have probably heard of. It is a numerical scale that ranges from 0 to 14 to tell us about how acidic something is. Now, the midpoint of that scale is our reference. I think with pH 7, we call neutral, and there's a very specific reason for this. Like, 7 seems like a very strange number to assign, and it is, really. Now, if you have a pH lower than 7, we're going to call that acidic. Acidic solutions have a lot of H+ relative to a pH 7 solution. If you have a pH that is higher than 7, we're going to call that basic because the solution is very, very little H+, and as a consequence of having very little H+, there's lots of hydroxide. Now, on this slide here, if I can get it to pop up, let me zoom in right here on the middle. Oh, there's a typo on this slide, and I haven't ever bothered to fix it because I just write over it, but not highlighter. So this right here, this should not be a 0. This should be a 1. All right, so what we're going to do is we're going to start at pH 7. There is some amount of H+ in water at pH 7, and we're going to define that as electrically, or not electrically, but pH neutral. So when you drink water, you are consuming H+. There's some amount in there, and that's safe. Sorry, my throat is extra dry today. Something is pH neutral if it has this quantity of H+, whatever that is. We're going to define it on the next slide or so. Because pH is a logarithm scale, concentration of hydronium, H3o+, or H+, is going to increase by a factor of 10 each time we take a step on the pH scale. So to get from pH 7 to pH 6, we have to increase it by times 10. To get to pH 5, we go times 100. This is all relative to pH 7. And so the pH will increase every time I multiply or divide by 10. I said increase, but it goes in the correct direction. So if I divide, it increases. And if I multiply, it will decrease. Excuse me. So you can see as we go up this way, whatever this quantity is of H3O+ that I have at pH 7, if I divide that by 10, I end up with pH 8. Divide that by 10, I have pH 9, and so on and so forth. And this goes forever. This goes forever in all directions. So you could have a pH that is 15. pH 15 would have 100 million times less acid than water would. And then pH -1 would have 100 million times more acid than pH 7 would. And so you could keep going in those directions. I mean, eventually you will hit a limit up here where you would start having like fractional molecules. So like there is an upper bound somewhere, but it's unobtainable. You cannot really go much further past pH 14 just because you cannot get that many hydroxide molecules in a container. Like it would be pure hydroxide at that point, and then trying to get more concentrated than that is virtually impossible. All right, let's look at some of these substances that match up with these pHs, because you're probably familiar with them, but perhaps you didn't know what their pH was, so this will be interesting for you. Pure water we define as pH 7. The reason that we say pure water is because this would be water without carbon dioxide in it. Water with CO2 is slightly acidified due to the presence of carbonic acid, which I'll show you in a little bit. That makes the rainwater pH 5.5. So water outside is actually pH 5.5, which is safe. It says right here acid rain is 5.6. This is wrong. Acid rain would have a pH lower than 5.6. It'd be more like 5.1 or 4.9 or something like that. When you pass urine from your bloodstream, not from your bloodstream, from your kidneys, I mean, it filters stuff out from your blood. Some of the stuff that is filtered out is small amounts of acid, proteins that can be acidic, waste products and molecules and stuff. The end result is the pH is slightly lower than pH neutral. Coffee is slightly acidic. Tomato juice and then common fruits get more and more acidic from there. So things that have citrus in them, so lemon, lime, orange, grapefruit, these are all things that have high, what we would say low pH. I keep wanting to say high, but these are lower numbers. You'll notice that as we get farther away, the things start to get more, we'll say hostile, I guess. So HCl in your stomach is pH 1. And then battery acid is pH 0. So these are things that like do not eat these things. Sometimes eat, and then safe to eat. Same thing exists going in the other direction here. So as we go up the pH scale, we get to things that are fairly safe. Toothpaste is pH 9-ish. It contains sodium fluoride, which removes H plus from the solution. Milk of magnesium is something that we take for indigestion and upset stomach, so this is used to neutralize stomach acid. We don't want it to be pH 14 because then it would start to deteriorate like your esophagus as you consumed it. And then as we go past that, these things are like cleaning the body and soul. These things past this, not for cleaning the body and soul. These will literally clean everything, as in like it will scrub you to death. So ammonia. Ammonia is very aggressive. I don't know about you. Whenever I need to clean something in my apartment, I get the Windex out because ammonia will cut through like virtually anything, right? Oh, the countertop's greasy. Ammonia. Oh, the windows are mucked up because the cats keep smudging their noses on it. Ammonia. Oh, the TV has like fingerprints on it. Ammonia. Like it just works, right? It starts cleaning stuff very effectively. And part of that reason is because it has a very high pH. Soapy water, same deal. Soapy water can have a pH of up to 12. Maybe not necessarily this high. It depends on the soap that you're using. And then past this, these are things that you really don't want to have in contact with your body. So, for example, bleach or oven cleaner. I have had to clean an oven and didn't have gloves available before, so I had to just be careful. And your hands get real slick after that because the pH is so high that it's saponifying your skin. Wash your hands real well. And then past that, this would be things like Drano. Like, this is pure sodium hydroxide at this point. All right. How do we get these numbers in the middle? Like, I don't know why it did that. Maybe it's indicating that pH 12 is the winner. Whatever. Oh, here's some practice problems, but these are easy, so I'm going to skip them. You can do these for your own practice. Very obviously, pick the ones lower than 7. Those are acidic. Higher than 7 is basic, so. How do we calculate pH, though? This is the formula that you need to use. Now, over here on my calculator, you'll see that I have this button here that says log. And so if I type some number in on the calculator, and I hit log, log performs a function that, if you don't understand how the numbers are working, seems to be totally random. Like, how do I get 3.13 out of 1,354? And the way that log works is that it is scaled to places. So if I do 1354 here, how many zeros do I have after the first digit? And that would be, well, I have 1, 2, 3 places. So when I log that, I'm going to get 3 point something. Let's suppose I did something like this, 1,000,005, and I hit log. So I should get a number that is like 1, 2, 3, 4, 5, very close to 6. And lo and behold, you totally do. So log is working with exponents. In fact, if I just did log of a... Oops, I have to hit the number first. If I did log of 1,000,000, you end up getting 6 as your answer. What if I do log of 1? Well, there are no zeros there, so I get 0 as my answer. Now, can I do log of a decimal? Sure. So if I do this, let's look for the place that is furthest over. How many places are before this? Well, 1, 2. So I should get -2 something. Oops, I gotta actually hit log. Oh, I'm sorry. That doesn't work if I don't know how to maths. Sorry. So I went from the wrong side. So here's my number. This is 1 decimal point from the ones place. So I should get -1 approximately. It'll be a little bit less than -1, which it is, because I'm not quite at 0.1. So the more zeros I have in here, the lower the log becomes. Can you have a log of a negative number? So if I do this, no, you cannot. So you cannot log negative numbers. So here is our formula for how we calculate pH. We're going to use the log 10 button on the calculator, which is this button right here that I've been pushing. It says log. Your calculator probably says log. There is another button that you don't want to push. That button says ln. Don't use natural log. The reason for that is because natural log does not scale in the same way. So if I type 10 for log, I should get 1. But if I do 10 for natural log, I get a different number because it's doing a different function. What natural log is doing is it's trying to take this other value up here, e, and if I natural log e, I get 1. So it is doing base e as opposed to base 10 for log. That's why I write this 10 here, is because I have studied a lot of maths, so it's just habit, really. All right, how do we get the pH out of this? You're going to input the concentration of H3o plus into the log, and then, and this is very important, you're going to flip the sign of it when you're done. This ensures that you will get a positive number because the concentrations that you're going to be putting in here are going to be very dilute. Note that the exception is if you put something super concentrated in here, you actually do get a negative pH, and that checks out. So let's suppose that you have a concentration of this, 1 times 10 to the minus 7. So, for example, let's suppose that our concentration is this. I'm going to log that, boop, and then I'm going to negate it. So this is the concentration of H3O plus or H plus in pure water, which is super, super dilute. We have defined pH around this value. What that means is that we're going to scale H plus up and down, and that's going to scale pH appropriately down and then up. based on what we do. Now, when you are doing pH, I want you to always express any number that your calculator spits out to 2 decimal places. So, for example, if you had like, I hit the wrong button there. I don't know, 5.4789 times 10 to the negative 4. So let's suppose that this was your concentration of H+, and so you go log, negate, and this is what your calculator spits out. Keep the first 2 decimal places. Note that I'm saying decimal places, which includes any 1s or 10s digits you have. So treat that as like your sig figs rules for decimal places for pH. We need at least 2 decimal places. All right. Now, if we take the pH of, say, a 1 molar HCl solution, we already saw that that's what that is pH 0. If I put in a larger number for that, so if I go like pH 4, or not pH 4, I'm sorry, 4 molar HCl, and then I hit log, I do get a positive number, which I then negate and it becomes negative. So this, as a pH as possible, but this is basically like, it's extremely uncommon to be dealing with acids of that strength. They do exist, and they actually are common as far as existing is concerned. However, we don't really use them. For instance, concentrated HCl is 14 moles per liter, but we don't really use it like that. You don't just pour it straight from the jug and like do stuff with it that way. Most of the time we dilute it to some degree. So your answers that you're going to be getting for your results are probably never going to be negative. And if they are, and you're like testing stuff with a pH probe, like, danger. Be careful. I'm going to write the equation up here again. So pH equals minus log of H+. When you enter this number into your equation, you can only enter the value that is given to you if the acid is a strong acid. Because, remember, a strong acid dissociates completely. So 100% of this dissociated. So if I said, oh, okay, well, my acid's concentration was this, then I know that this ends up being that, because 100% of it dissociated. Now, for a weak acid, if I do this, and it's 0.125, I don't know what percent dissociates without doing a lot of algebra. And that algebra would take me, well, let's just put it this way. The calculations that are involved in calculating how much H plus are found for a weak acid, I do in engineering chemistry. I did that topic over the course of, and I shit you not, 4 weeks. Would you like to do some problems that take 4 weeks to learn? No, not on the last day of lecture. What the fuck is wrong with you, Professor Wes? Nobody wants this, so we're not going to do that. I'm serious when I say long drawn out math. It's a lot of work. So if I give you a weak acid, I cannot give you a concentration of weak acid and expect that you would be able to calculate H3O+. So instead, what I have to do is, in a weak acid, I will do the calculation for you, because I can do it really quickly. And I will tell you H3O+. Now, it's still important for you to realize that an acid is a weak acid, so that you know, oh, okay, the number that he's going to give me is H3O plus. All right. Now, if you need to know the pH of something that's a base, remember the formula is still this. However, if I'm using something that contains lots of hydroxide, it would be basic. Knowing the concentration of hydroxide is sometimes more convenient. And so we can devise a different formula that revolves around POH, and it is literally the same formula. So if you need to use the concentration of hydroxide, you could find what's called the POH. And the POH works exactly the same way as pH. You just enter whatever concentration of hydroxide you have in the equation, take the log of it, and then negate your answer to flip its sign. How do you get POH to turn into pH, though? Because pH is the thing that we all use as our reference. And the answer is that we just use this equation. 14 minus whatever your POH was is your pH. Or in other words, if you add the pH of a solution and its POH together, you always get 14. And that checks out because a neutral solution would have pH 7. What would its POH be? Well, it's neutral, right? So it'd still be 7. And 7 plus 7 is 14. All right. So let's do an example here. What is the pH of 0.250 molar sodium hydroxide? Oh, that doesn't help anybody. Hold on. Let's get this on the screen here. All right, so let's write down our formulas. So we know that we've got pH oh, wow, I really need to reboot my PC here. There we go. So we got this formula. We've got this formula. Oh, fuck's sake. And we've got this formula. Oops, we'll do it. We'll write it like this. Okay, so we know the POH of our solution by saying, okay, sodium hydroxide is a strong base. It will dissociate completely. So 0.250 molar sodium hydroxide will dissociate completely into these two things, of which I will have 0.250 molar both of these. So the POH would be negative log of hydroxide, which would be negative log of 0.250. Now, for units inside pH, we just ignore them. And so that would be, when I type this in my calculator, 0.250, we're going to log that, and then we're going to negate it. And then we're going to keep 2 decimal places, so 0.60. And then we'll say 14 minus POH equals pH. And we're just going to put this number right there. So the pH of a solution of 0.250 molar sodium hydroxide would be 13.40. It would be very, very high pH. And that checks out because sodium hydroxide is a base. So its pH should obviously be higher than 7, and it is. All right. So this is going to leave us with one question. We're going to do that in this section, or this question right here. So I want you to skip this one for now, but we're going to come back to the second question. How do I find the concentration of H3O plus from a pH? But what I want you to do instead is do problem 1 and problem 3 here. So go ahead and do the first problem here. HCN has an H3O plus concentration of 5.25 times 10 to the minus 5. Find its pH. That's a weak acid, so I've given you its concentration of H3O plus. And then I want you to tell me what the pH of 14 molar HCl is. And then calculate its POH. All right. I'll give you about 5 minutes to do those, and then we'll do number 2 after that. One more minute, we'll go over the answers. All right, let's go over the results here. So we'll go over here. I'm going to leave our formulas on the screen here and just go like that. Let me make a new layer real quick. There we go. All right, so if I want to figure out what the pH of this is, that'd be negative log of 5.25 times 10 to the minus 5. And what does that equal when I punch that in my calculator? So there's our concentration. We're going to log, and we're going to negate. So this would be a pH of 4.28. All right, we're going to come back to problem 3 in just a second. All right. Concentrated HCl is 14 molar, so what would the pH of something that's 14 molar be? I mean, you just get this as your equation, which would be, I'll type in 14, we'll hit log, and then we'll negate it. And so there's the pH. Actually, I guess this would be 1.15, huh? Which is, this is sort of the lowest pH that you can get to, is like around pH 1.1, 1.2. And the reasons for that have to do with physics. Like, you cannot physically cram more acid into the container. Like, there's just, like, eventually you run into the constraints of, like, actual space. Like, if you could just jam individual protons together in, like, I don't know, like a star or something, then yeah, the pH would be lower. But, like, that isn't a solution and it doesn't really make sense. And then what we can do is we could say, well, 14 minus POH equals pH. And so if I solve for POH with negative 1.15 here, I could get the POH. And what that ends up happening when I do that is I get this. All right. How do I do this second problem here? What do I do if I need to figure out H3o plus? And I'll write H3o plus here. So if I know this, how do I solve for this? And the answer is that we have to undo log. For every mathematical function, there is an undo. If I have something that I've added to a number and I wanted to undo it on accident, my undo would be to just subtract it, right? So if I add 2 to a result and I say, oh, I added 2 too many, I'll just subtract 2 and that gets rid of it, right? What about if I multiply? What's my undo? Let's divide, right? What if I raise something like the power of 2? Like I squared something. How do I undo squared? Well, you square root, yeah? So every function has an undo. What is the undo for log? And the answer is to do 10 to the power of whatever log expression you have. And that's why I write this 10 here, because this 10 ends up here. So in order to undo log, what we do is we say 10 to the power of everything on both sides. Now, the first thing I'm going to do is, before I do that, because this is trapped in my exponent, I'm going to move this minus over here so I can get everything by itself. So then my expression right here would become 10 to the minus pH equals, the 10 to the and the log cancel out, and I get the concentration of H3O+. So how do I figure out this number in our calculator? What we're going to do is we're going to type in the pH, which was 7.30, and we're going to hit this button right here, 10 to the x. Notice this is next to the log button. Yeah, there's a reason for that. They're inverse functions of each other. So when I hit this button, well, first I got to negate it, and then I'll hit this button, and I get 5.01 times 10 to the minus 8. And that's the concentration of H3O+ in my acid, or in the solution that has pH 7.30. So that's what the concentration of H3O+ is in your bloodstream. It's about half as acidic as water because it's got half of the H3O+ in there. All right. So just as a little demonstration problem, I want you to do the following. So we'll leave that on the screen for you. So if I have pH equals 3.62, how much H3O+ do I have? So I'm going to let you calculate that. And I'll give you like 2 or 3 minutes to play around in your calculator to get the answer. I'll leave the formula on the screen here, 10 to the minus pH. So go ahead and do this, and we'll go over the answer in about 2 or 3 minutes. One more minute, we'll go over the answer. All right, so to figure out the amount of H3O plus in here, we would go 10 to the minus pH. And so we'll just type it in the calculator. So 3.62. And we're going to put a negative in front of it, and then 10 to the x. And there you go, 2.40. That's 10 to the minus 4. There you go. All right. All right. Before we take our break, let's... Well, first, here's the homework practice for pH. So, the pH section is really just punching in things in your calculator and going back and forth between the two things. Before we take our break, let's talk a little bit about pH. What do we care? All right. Anywhere on Earth that involves water has relatively a neutral pH. So, for instance, in the year 2000, when I got this data, I didn't write this slide in the year 2000. This was just the data I found. I actually wrote this slide for a job interview at Edmunds, and they actually really liked this presentation. So, probably because I included Edmunds, Washington in there. So, we have a bunch of pH values here. So, ocean water in the year 2001 was measured about 8.1. Rainwater is approximately 5.6. And if we measure the pH of tap water, it's roughly 7.5 or so. Now, these numbers are what I would call typical. If you're in the typical range, you observe typical effects. For instance, if I were to spill rainwater outside, nobody would be like, "Oh no, it's rainwater. No, how awful." Nobody would give a shit, right? It's just rainwater. But let's suppose that I went outside and I accidentally spilled hydrochloric acid. That could actually be kind of I'm using the word interesting here, but in reality, that could be kind of dangerous, right? I could dissolve something that I don't want to. And so we're going to talk about that in this section really quickly here. So why is rainwater slightly acidic? I said earlier that it is because when we combine H2O and CO2, you get an acid. And that acid is carbonic acid. This is the same acid that is in your fizzy beverages, such as Polar Seltzer. That's the important fizzy beverage. But other fizzy beverages like Coca-Cola, Pepsi, Sprite, Mellow Yellow, Crystal Pepsi. I'm trying to think of the most esoteric beverages now. And I just kind of can't. Anyway, we put CO2 to carbonate beverages, and it becomes acidic, which gives it the little tart taste. Rainwater does this on its own because there is atmospheric CO2 present. When we exhale, we emit CO2. When we combust fuel with our cars, we emit CO2. That gets into the water vapor to produce carbonic acid. The end result is that we get pH 5.5, 5.6 rainwater. And that's okay. Our environment is acclimated to that because CO2 has always been in the atmosphere, right? It's what plants use as food, basically. Now, acid rain can form when we have things that are more acidic than CO2. For example, SO2. Sulfur dioxide will mix with water to form sulfurous acid, which is a weak acid, but it's actually one of the relatively strong weak acids. The same thing can happen if you get smog in your air. So NO2 can combine with water to make nitric acid. If there's NO, that'll combine to make nitrous acid. And those are all acidic, so they will lower the pH of water considerably. So this is called acid rain. Acid rain forms from smog, it forms from industrial pollution, and the end result is that the pH for rainwater decreases from 5.6, which is normal, to much lower, so say 4 or so. On this chart, which was produced in like 1997. And again, this is just where I was looking it up online and this chart was available. The pH of rainwater was analyzed for various locations across the United States. And you'll notice that the red region centers around one very specific location. And that location is right here. What is that city that I have drawn an X through? And what are they popular for in terms of things that they produce? I'll give you a hint. It's the name of their football team. Any idea? Go ahead and type it in the chat. We'll see if people know. Last quarter when I asked this question, people were like, Pennsylvania? And I was like, yeah, that's the state. I want the city. And let's see if anybody knows their geography here. I have been to the city, and it's actually very nice. Like, I genuinely liked going to this place. Any idea at all? Everybody knows. That's correct. It's Pittsburgh. This class is informed. Well done. What does Pittsburgh make? Well, I mean, you got the Pittsburgh Steelers, right? So they produce steel. What does the steel industry produce besides steel? That's right, it's pollution. Hooray. Now, interestingly, the pollution comes from the iron that is smelted, and in the iron are impurities such as sulfur. That sulfur can then be emitted into the atmosphere as sulfur dioxide, which causes acid rain. Now, it's not that Pittsburgh is doing this to its entire surroundings. So you don't have to go to Pittsburgh and be like, haha, Pittsburgh, suck it, Ohio. Because really what's going on is that there's just industry everywhere here. So, and that's because we created all this industry way, way, way long ago, because honestly, that's where the country started, was over there in that general area, like Delaware and so on. But an important environmental consequence of this is that the pH of this region right here is much lower than that of neighboring or other regions across the country. Also, all of our air currents sort of go in this direction. Yeah, I also say suck at Ohio anyways. Ohio's kind of lame. Sorry about anybody out there who's watching this who's from Ohio and is like, hey, I like Ohio. Your state is shit. Come to Washington. It's way better. Do you know what the temperature is today in Washington? It's about 60. I'm thinking about turning my heater on in June. In fact, I'm going to do it right now. Oh, look at that. It's so warm. I have a heater. Anyway, that's enough taunting Ohio. If you have things outside that are susceptible to acid corrosion, then that could be bad in an area like, say, Pittsburgh or the East Coast, if it's exposed to acid rain. So on the screen here, I have a picture of a statue that has been made out of limestone. And you can see that the statue seems to be melting. And this is due to the gradual effects of acid rain washing over it and then just basically dissolving the finer detail here. So this looks like a statue of... Honestly, I don't know. It's obviously a person, but I can't tell their features anymore. I was going to say, maybe it's like because I was going to say it looked like a man, but then this right here, I was like, I don't know about this lock of hair, so... And then I don't know what this is over it, so... So, anything made of limestone or marble, which contains a basic solid calcium carbonate, will react with an acid, like acid rain, and then it'll undergo erosion. Metals are susceptible to rusting when they're exposed to acids as well. So anything that is made of metal, ironically, the steel that Pittsburgh produces is susceptible to corrosion and rust due to the acid rain that is produced. So obviously, these are not desirable things for civilization because we produce metals. We produce really cool art out of sculpture, and those sculptures can use basic materials like plaster of Paris and stuff like this. And we don't want that to be destroyed by our hubris. But also, it's Ohio, so, you know, screw those guys. All right, we're going to take our break while I go and delete the angry comments by people who live in Ohio. So, 10 minutes. We'll come back. We'll finish up. We're going to go straight to the buffer section next. We'll see you in a bit. Alright, there is not much time left. So, what we're going to do is we're going to skip this section, go to this section. We're going to talk about buffers, and if we have time, we'll go back to aqueous salts. Because buffers are much more important. Alright. Your body is exposed to acids all the time. You're also exposed to bases, but acids all the time, pretty much. So if you drink carbonated beverages... Oh, there's all the rare sodas. Diet Cherry Coke. That doesn't sound like something that anybody would drink. Diet Crystal Pepsi. I don't know what Nehi Peach is, but yeah, there you go. So these are all probably acidic because they all contain carbonation. And so if they have other things in them, so for instance, Pepsi and Coca-Cola have things like phosphoric acid used as a flavoring agent. That makes it very, very tart, but it also lowers the pH to about 2.5 or so. Not to mention that your stomach contains stomach acid, which is about pH 1 to 2. Now, it turns out that your blood needs to have a pH that's very specific in order for it to do its function. And that pH is 7.4. If you go too far above or below that, you die. That's very bad. Now, the amount of acid that would be needed to go from pH 7.8, or I'm sorry, 7.4 to 6.8 is about the amount that would be contained in roughly a milliliter of soda. So 1 milliliter. Can you imagine how small 1 milliliter is? That's like an eyedropper full. Yeah, that's enough acid in that soda to kill you if it got in your blood. Because your pH would just be way too low, and then all of your proteins would denature and you'd die. So, why can we consume soda safely? Why can we have acid in our stomach safely? And the answer is buffers. Buffers are a mechanism that resists a sharp change in pH by creating a unique environment. And that unique environment is chemically sort of tied to a pH range. So, I have a video here that's going to show us how a buffer works. And let me see if I can load this. There we go. I don't want to have audio because we don't care about that. I'm going to talk over him anyway. Buffer. Okay, so on the left here, you can see that we have an unbuffered solution of distilled water. On the right, we have what is probably a dihydrogen phosphate and a hydrogen phosphate buffer to keep the pH around 7. We also have this pH paper or strip indicator for the color that is used. So because it's green right now, it's about pH 7 or 8. We're going to add HCl and sodium hydroxide to each of these in turn. So this is 1 molar HCl. This is pH 0. We're going to add 1 or 2 drops to this. So drop, just one drop. And this is what happens to the pH. Whoops. Yeah, so when I was saying 1 milliliter would kill you, yeah, that I wasn't kidding. The pH is now 1. Because it's so concentrated. Now we're going to try and do the same thing to the buffer. So 1 drop, 2 drops. And nothing has happened at all. And the reason for that is the buffer provides a buffer for pH. Something in the buffer is reacting with the acid that we're adding. So he's going to add this very slowly. I guess the camera's going to go out of focus, but that's okay. Now he's just adding more and more drops. So drip, 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 drip. And the pH isn't changing. So now he's just going to go ham on this and just like empty the whole thing into it to try and get the pH to change. And it is very slowly moving in the direction of pH 7. So it's no longer as green as it was when it started. It's only just yellow. I mean, you could probably make an argument that you might even be close to like pH 6. But it's certainly taking way longer to do this than it took for the unbuffered solution. Yeah, here we go. Now we're more at pH 6. So it took a while to get there. Okay, dude, we get the point. Cool. Okay, so that took a lot of acid added. So now what we're going to do is we're going to add sodium hydroxide. Sodium hydroxide is pH 14. And when we add 1 drop of that to the unbuffered solution, it will not only neutralize the HCl that we've added with 1 drop, but it goes way past it, and now we're at pH 13. Actually, we're probably closer to like pH 9 or 10 or so. Oh, now we're pH 7. Okay. So that 1 drop roughly neutralized all the acid we put in there. So we'll do 1 more drop. And now it should be dark, dark blue. And yeah, there you go. So this is now pH 8, 9, 10, 11, 12 plus. 12 plus, we'll say. We're going to add sodium hydroxide to the acid here. Or I'm sorry, to the buffer that we have acidified here. And let me get the marker out of the way there. And it's, look how many drops it takes to do this. Drip, 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 drip. Barely affected. And so now it's fast forwarded. So you can tell that just by the presence of whatever a buffer is, the amount of acid and base you have to put in to change it is significantly increased. And that's crucial for biology. We do not want our biological systems to be exposed to rapid changes in pH because proteins are very pH specific. And if you are above or below the safe threshold of pH for the bloodstream, the effects can be deadly. A buffer is a combination of 2 things. Those things are the following. Some sort of weak acid is required. It has to be a weak acid. If it's a strong acid, this does not work. The second thing that's required is that you need the conjugate base of the weak acid, which would be a weak base. You need to have these 2 things together to form a buffer. This is a common buffer that is used in biology. This is called the phosphate buffer. And the reason that we use this is because this is the buffer that is used in intracellular fluid. So this is the pH of cells, basically. It's roughly 7.1 or so. And the way that we get this is we combine H2PO4 minus, a weak acid, with HPO4 2 minus, a weak base. Now, these will commonly be prepared and sold as something like this. So this weak acid down here would be this. You'll notice that I have potassium that's added in here. And that's because K plus is used as the counter ion to these negative charges. I can't put something that is only negatively charged in a bottle. I have to have some positive ion to counteract that, right? Otherwise, all the minuses would repel each other and would not stay in the bottle. So these substances are often sold as potassium salts because potassium is abundant and cheap. So you might hear potassium dihydrogen phosphate, which would be this guy. That's our weak acid. And then potassium hydrogen phosphate, which is this one. You might also hear the words monobasic and dibasic, which is just how many H's have been taken off. Now, because we are using these two substances, these substances which are conjugates of each other differ by H+. And as a result, adding H+ means that I will turn something into something else that already exists. So if I were to add H+ to my reaction, then according to Le Chatelier's principle, I would drive the reaction in this direction, right? We covered Le Chatelier at the end of Chapter 9 in one of the extra lectures that I had to link. So if you haven't watched those extra lectures, make sure you go back and do that. If I add a base, that'd be like removing this, and then the reaction would be driven in this direction. And really all we're doing is we change the amount of these things that we make when we add acid or base. The acids and bases that are added react with the parts of our buffer, turning it into the other component of the buffer, and so the pH doesn't change very much. So that's the magic of the buffer. The buffer allows the system to remain roughly the same pH. So, all right. For each of these combinations, excuse me, what I want you to do is I want you to tell me, is it a buffer or is it not a buffer? So, look at pair number 1. Could I mix those two things together to make a buffer? Remember, a buffer needs to be a weak acid and its conjugate weak base. So, I'm going to number these for you, 1 through 4. And tell me which ones you can make into a buffer and which ones would not form a buffer. One more minute, we'll go over the answers. All right. So looking at these right here. So first, let's look at all the acids here. So we've got acetic acid. We've got hydrochloric acid. We don't have an acid here. And then we've got bicarbonate, which could be a weak acid. So immediately number 3 is out. There's just no acid. Well, we have our weak bases, so that's obviously not going to work. Number 2, we have HCl. That's a strong acid, not a weak acid, so HCl is a strong acid. The other 2 will work. So we've got acetic acid and then its conjugate acetate. Those are a weak acid and its conjugate base. And then down here we've got bicarbonate and its conjugate carbonate. These differ by H+, and they're both weak acids and bases. So this would work. You could make a... excuse me. You can make a bicarbonate carbonate buffer, no problem. In fact, that buffer is pretty common because the pH of bicarbonate is roughly 7 or so. All right. So now what we're going to do is we're going to go back to this phosphate buffer that we had here. And what we're going to do is we're going to add strong acids and strong bases to it and see what happens. Because the point of a buffer is for it to resist changes in pH. A strong acid or strong base should cause the pH to change very rapidly, but we're going to see how this works. If I add hydroxide, hydroxide is a strong base. What the strong base does is it's going to react with the acid part of the buffer. And when it does that, I'm going to take one of the H's off of here, react with this to form water, and what I end up with is the weak base part of the buffer. So I turn my weak acid part of the buffer into the weak base of the buffer. And because I already had that weak base there to begin with, making a little bit more of it, changes the pH very little. So instead of the pH going up by a lot, the pH goes up very little because we neutralize the strong base and turn it into a neutral compound by producing a very weak base. Now, the same thing will happen if we add acid. It's just that instead of the acid reacting with H2PO4-, it would react with HPO42-. So that would look like this. So here's our acid we're adding. I'm going to react this with the weak base part of the buffer, and I'm going to create the weak acid part of the buffer as a result. So the end result is that buffers are excellent at negating the effects of great pH changes. So if you have consumed something acidic, such as, say, a soft drink, and a little bit of that acid gets into your bloodstream, it's not a problem because the buffer will neutralize it, and the pH will change very little. Now, if you injected soda pop right into your veins, that'd be very, very bad, obviously. Don't do that. But biologically speaking, if you consume acidic or basic substances, they hit your stomach, and then when they go through your intestines, they hit this buffer as they're absorbed into the bloodstream. The effects of acid are diminished significantly, keeping the pH of blood around a very tight region, and thus the proteins in your blood and cells and elsewhere are able to do their function. Thanks, buffers. So all we are really doing is just when we add H+, we are just changing it back and forth. So if I add H+, it does this. If I add hydroxide, it does that. Now, it is possible to add so much H+ or OH- that you will consume all of one part of the buffer. The buffer is not infinite in its capacity. The buffer does have a limited capacity. For instance, if I reacted entirely all of the KH2PO4, then if I added more acid to that, there would be no buffer left to react with, and the added acid would then just change the pH very, very rapidly. And so the pH of that would look something like this. So if my y-axis here represents pH, and we'll say if I go in the right direction, I add base, and if I do this, we're adding acid. At some point, the effects of the buffer don't work anymore, and the pH just drops. Same with this. So at some point, the pH effect on the buffer or by the buffer fails, and the pH just rockets up. So there is a region in the middle where the pH changes very little, and that is due to the buffer. All right. I think there's a homework practice after this. Yeah, there we go. So let's look at the carbonate buffer, or bicarbonate buffer. So this bicarbonate buffer is formed from CO2 in your blood, which comes from basically your cells. Your cells put the CO2 into your bloodstream. Your bloodstream transports it to your lungs, but some of the CO2 is used to maintain this buffer. So let's suppose that you have a buffered solution of H2CO3 and H3O3-. What I want you to do is write out the reaction for what part of the buffer will react with HCl and what part of the buffer will react with NaOH. And then I've already spoiled the bottom question for you. Like, oops. I already told you where you get all this stuff from. So we'll go over the answers to the top questions in about 3 or 4 minutes or so. One more minute, we'll go over the answers. All right, so let's write out the equations here to show our carbonate buffer reacting with this. So we'll do something like that. That's probably fine. All right. So let me just do. Can I see? Oh, I can. That's perfect. Okay. So I'm going to react something with the weak acid part of the carbonate buffer. So if I react this with hydroxide, which would be a strong base, I would produce H2O and bicarbonate. Because I would take one of the H's off of here, put it there, and then it ends up there. So this bicarbonate carbonic acid buffer will react with hydroxide and reduce its effects on pH. Now I can do the same thing with acid. That's going to react with the bicarbonate part to produce carbonic acid. And you'll notice that in our reactions, we are always producing the other component of the buffer. And so all that's really happening whenever I react with acids and bases in a buffer is that I just turn one component of the buffer into the other. I'm just changing the ratio of what's present. All right. And again, where does all this come from? We just said it. It's from CO2 that your cells produce from the combustion of oxygen with some sort of molecule that would provide energy. So like, say, glucose, for instance. We produce CO2. That CO2 then gets transported to the lungs, but on the way, it can be used as part of the buffer. Now, how do you think you could run out of buffer? You might have heard of people who hyperventilate. This was very common in like sitcoms and like cartoons and stuff. They would show a character with a paper bag and they would just breathe into and out of it rapidly. The effect of that was supposedly that they didn't have enough CO2 in their bloodstream because they'd used up all of that part of the buffer. So, not that you would understand that like that's supposed to make a biology joke, but and it's more that like somebody is like panicking or something and then they just start inhaling into a paper bag. But biologically what the effect of that would be is that you have too little CO2 in your body, and so that's how you'd get some of it back, or at least recapture it. Now, alternatively, if you exercise a lot and you generate lots of CO2, what do? Well, you start panting and wheezing, right? Like you're out of breath. You inhale and exhale really quickly. What your body is trying to do in that case is it's saying, "Oh, I have way too much of my buffer, way too much carbonic acid in here. I need to get rid of some of the carbonic acid. I'm going to expel that as CO2, from the lungs, and your lungs do that by exchanging the CO2 every breath you take. That is my understanding of biology, as limited as it is. So. All right. I don't think that there's going to be enough time to really go over the aqueous salts and pH part. So, yeah. I guess what we're going to do instead is we're just going to go to the last slide, which is we get to celebrate. Hooray. There are no more slides. There's no more Chemistry 121. Just assignments that you have to turn in. So, there we go. What's going to happen here is that you are going to take exam number 2 on Friday or Saturday if you've requested to take it on Saturday. You do have a lab worksheet number 5. That is due next week. Check the syllabus for the due date on that. That worksheet is just a solubility worksheet, which is very straightforward. I don't think that there's really much I need to talk about for that. Next week is a final exam, which I'm going to post. On Monday, I will ask if you need me to move your exam date for the final. Please email me if you have a request to move the exam. I do need the final exams done by late Saturday. Sunday, I think... I don't actually know where my exam is scheduled. I think plus or minus 1 day of whatever's listed in there. Try to avoid using Sunday, just because I need to have all the grades in so that I can release the grades. I believe grades are due like Tuesday after finals, so. Sorry, just a second. I'm hitting a button so that my monitor doesn't turn off. Yeah, I think that that's it. So there are no more lectures. We do have a review session next week, so I will post an announcement about that. It'll be on Tuesday at the normal class time, but other than that, that is everything that I have prepared. So I will hit this for the last time here. Where is the file? There we go. We'll hit this for the last time. And we'll just let it play all the way out. So thanks again. I hope that you found the lectures enjoyable, and I hope you learned something. Take care.